Guys, in this problem we have 82 students. First, we subtract the 12 students who take neither subject, leaving us with 70 students who take at least one course. Using the exclusion principle, we add those taking English and math, then subtract the total of 70. This shows that 35 students are taking both subjects. So the answer is 35. For part B, we start with 97 students and subtract 15 who take neither, giving us 82. Since 53 take exactly one subject, the remaining 29 must take both. Letting math be x and English be 2x, we set up our equation. 82 equals 3x minus 29. Solving for x, so it will be 3x equals 111. So x will be equal to 37. So we find that 37 students take math and 74 take English. Now let's look at story data. To find how many people bought all four kinds, we use the 4 set inclusion-exclusion formula, summing up the singles, doubles and triples. We get we get 891 minus or unknown equals 890. So exactly one person bought all four kinds of juice. So it will be, here's the minus, will be equal to 1. To find who's bought only grapefruit juice, we take the initial 100 people and subtract those who bought it with other juices. So it will look like that. After adjusting for overcounting using the triple and quadruple intersections, we find that 34 people bought only grapefruit. So let's move to the next problem. Next, exactly for two kinds of juice, we use the formula for exactly m sets. We take the sum of doubles, subtract 3 times the triples, and add 6 times the quadruple intersection. So this calculation gives us a total of 351 people. And let's move to the next final problem of this task. For those who bought more than 2 kinds, we add the people who bought exactly 3 types to the one person who bought all 4. So that gives us 29 people in total. In exercise 12, first problem A. In this task, we need to find how many integers less than 500 are relatively prime to it. We use Euler's totem function. So first factorize 500 into 2 squared times 5 cubed. And then multiply 500 by 1 minus and half and minus 50. And the result will be 200. To be equal to 500 multiplied by 2. That will be equal to 200. So the result will be 200. And let's move to the second problem of this task. Here, let's do the same for 9975. Its prime factors are 3, 5 cubed, 7, and 19. Applying the same formula, we multiply. Applying the same formula, we multiply this number by these fractional factors. So the answer will be 4,320. That there are this much integers relatively prime to this number. Let's move to section 2 to task 6. Here we need to find the number of palindromes using 26 letters of the English alphabet. So the part A, let's solve to part A. A palindrome looks like that. We choose L1, L2, L3, L4 and L5 are fixed by our first two choices. So calculation will look like that. And second part B. Pattern is L1, L2, L3, L4, L4, L3, L2, and L1. We choose the first 4 letters, the rest mirrors them. So the calculation will be 26 and 4 in the answer will be this. And let's move to for part C. Here sum of polygons for lengths 1 through 8. So the lengths 1 and 2 will both have 21 variants. Lengths 3 and 4 have 21 square variants. 4, 5 and 6 have 26 group variants, and lengths 7 and 8 both have 26 4 variants. So total will be which gives us reaching a total of this number. So here is the task 6. On to task 10, we are looking for the total numbers of 7-digit telephone numbers. So the first 2 digits have 8 options each from 2 to 9. Let's just digits 1 and 2 are of range of 2 and 9. 8 choices each. 2, 3, 4, 5, 6, 7, 8, 9. Digit 3. Range from 1 and 9. 9 choices. Here is the 9 choices. And digits 4, 5, 6, and 7. We have range from 0 to 9. It's ranged like 9 choices. 10 choices. 10 options for each. So using the multiplication principle, we multiply 8 by 8, by 9, then by 10 to the 4th power. So total will be 8, which gives us 64 multiplied by 9, multiplied by this, and this gives us 5,760,000 possible phone numbers. Now let's move to task 12. Here we need to find all pairs. Here we need to find all pairs of adjacent squares on a standard chessboard. So adjacency can be either horizontal or vertical. In each of the 8 rows, like there are 7 vertical pairs, adding another 56. So 8 multiplied by 7 is 56. Vertical, it's for horizontal pairs. For vertical pairs, in each of the 8 columns there are 7 adjacent pairs, so it will be the same. 56. Adding this together, we find there are exactly 112 ways to select 2 adjacent squares. Task 15, we need to find 3-digit numbers that include both 2 and 5, excluding the digits 0, 3, and 7. So the set is 1, 2, 4, 5, 6, 8, 9. There are 7 allowed digits. The number must contain at least 1, 2, and at least 1, 5. So combinations will be the first case where x is any of the 5 other digits. So permutations 3 factorization x will be 6 for each x. Total 5 multiplied by 6 is 30. In second case is permutations 225, 252, and 522. Total 3. And third case is also total is 3. So total will be, in this test, total will be 30 plus 3 plus 3 equals 36. And adding them up, we got a total of 36 numbers. This last section, first task 3. First, let's represent our list of natural numbers as a1 through an. So list of numbers will look like that. To prove this, we need to look at the prefix sums we defined as the sum of first k numbers in the list. This gives us exactly n different sums. So next we consider the reminders of these sums divided by n. There are n possible reminders from 0 to n minus 1. If any of our sums has a remainder of 0, then that sum is already divisible by n. So, and we have found our consecutive string. So possible reminders are 0, 1, 2, and n minus 1. If any is sum equals to 0 more than, so it will be done. So, but what if none of the sums are divisible by n? In that case, all n sums must have reminders between 1 and n minus 1, since we have n sums but only n minus 1 possible reminders. By the pigeonhole principle tells us that at least two sums must share the exact same reminder. Let's call them Si and Sg. So finally, because Si and Sg have the same reminder, the first difference must be divisible by n. We are left with the sum of elements ai plus 1 to ag. This is a string of consecutive numbers whose sum is divisible by n. This is divisible by n. Right, let's look at the problem 5. We have a large square with a side length of 2, and we're placing the 102 points inside it. So number of points is 102. Side of length is 2. And first let's divide our 2 square into 4 smaller squares, each with a side of 1. Why? Because the maximum distance between any 2 points in a 1 by 1 square is a diagonal, which is exactly 2 square. Well, we apply the pigeonhole principle. We have 102 points, our pigeons, and 4 small squares, our holes. If we divide 102 by 4, and we get 25.5, this means at least one small square must contain at least 26 points, since all points in that square are within square 2 of each other, so the answer will be 26. And let's move to the second part of this task, part B. This was part A. Now for part B, how close are at least 2 points guaranteed to be? To find the best guarantee for just 2 points, we want to create as many holes as possible. We need more than 100 cells to use 102 points effectively. We will divide 2 and 2 square into 1 or 10 and 10, 100 small squares. Each small square side will equal to 0 and 2. So therefore those parts, these 2 points are diagonal of tiny squares, so max distance will look like that. So this is the answer of this problem. For task 12, Linda is studying for an exam over 6 weeks. That's 42 days in total, because weeks have 7 days. And let's define S as the total number of hours she has studied from day 1 up to day K. Let A be hours studied on day I, since A equal or more larger than 1 and is a whole number. So this is hours studied on day I. Let's S be the cumulative hours. We know that 1 is 1 is 42 are less than or equal to 50, because we know that here total study time it as most 50 hours. Now we want to prove there is a period where she studies exactly 33 hours. To do this, let's look at 2 sets of numbers. The first set is her 42 cumulative sums. The second set is 2 same sums but with 33 added to each one. This gives us another 42 values. Altogether we have 84 numbers, because adding this 82, so 84 I mean. However, the small possible value is 1 and the largest possible value is 50 plus 33, which is 83. From 1 to 50 plus 33 is equals to 83. Since there are because we have 84 numbers but they all fall within a range of only 83 possible values, the pigeonhole principle guarantees that at least 2 of these numbers must be identical. Since the sums in each individual set are strictly increasing, one number from the first set must equal to number from the second set. This means Sg equals Si plus 33, therefore the hours studied from day I plus 1 to day J total exactly 33 hours. So goal achieved. This is the result of this task. In this last problem, let's look at this problem. You have the set S of 8 prime numbers. Here it's 8 elements. Shows that there are 4 different non-empty subsets that have exact sum. So the number of non-empty subsets will be equal to 255, and minimum possible sum is 2, because that's how no smallest sum is 2 and the largest sum of elements 77, because 2 3 plus 5 equals to 77, and this gives us 76 possible values for our sums. If we apply the pigeonhole principle and distribute 255 subsets into 76 possible sum values, we divide 255 by 76, which give us more than 3 and 3. Therefore, at least one sum must share it by 4 different subsets. Proof complete for part A. Let's write part B. Now for part B, there are 2 non-empty subsets with the same product. The answer is no, and here's why. Every number in our set S is a prime number, and every integer has a unique prime factorization. Since we are creating products by picking different combination of these primes, each unique subset will produce a unique product. For example, the product of 2 and 3 is x. From fundamental theorem of arithmetic, every integer has unique prime factorization. For example, a3, b 6, and b is 5. So, for example, product of 2 and 3 is 6, and there is no other combination of primes from our set that can multiply to 6. So every subset has a unique product. So it's the answer. Thank you.